For understanding power factor and power factor correction capacitors, several resources are available. These encompass technical books, IEEE standards, technical papers and articles, online resources, and manufacturer's documentation. Considering technical books, firstly, the Power Factor Correction Handbook by G.T. Haight, published by IEEE Press, offers a comprehensive overview. Secondly, Power Factor Correction Techniques in Electrical Systems by A.B. Kulkarni and S.A. Coppard, published by Marcel Decker, delves into various correction methods. Thirdly, Electrical Distribution Engineering by Anthony J. Pansini, published by Taylor and Francis, provides insight into power factor within the context of electrical distribution. Fourthly, the Handbook of Electrical Engineering by Ellen L. Sheldrake, published by Butterworth Haneyman, covers a broad range of electrical engineering topics, including power factor. Moving on to IEEE standards. IEEE Standard 519.2014, titled IEEE Recommended Practice and Requirements for Harmonic Control in Electric Power Systems, is crucial. Harmonics often contribute to poor power factor, so understanding this standard is essential. Also, IEEE Standard 18.2017 is the IEEE standard for shunt power capacitors. This standard provides guidelines for the application, installation, and testing of shunt power capacitors used in power factor correction. Several technical papers and articles provide in-depth analyses and research findings. Firstly, Power Factor Correction Capacitors, a comprehensive review by S.K. Carr and S.N. Badra, published in the International Journal of Electrical, Electronics and Data Communication, offers a detailed examination of capacitors used for power factor correction. Secondly, Power Factor Correction Techniques Capacitors and Applications by A. Ghosh and G. Ledrich, published in IEEE Proceedings. Generation, Transmission and Distribution, explores various techniques and applications of power factor correction. Thirdly, a review of power factor correction techniques for induction motors by P. Thong and B. S. U. Alporn, published in the International Journal of Applied Engineering Research, specifically addresses power factor correction in induction motors. Numerous online resources can provide introductory information and practical guidance. Firstly, Electricafa.eu provides an article on power factor and power factor correction. Secondly, Eaton offers a guide to power factor correction. Thirdly, T&D World offers an article on understanding power factor correction. Manufacturers provide documentation and resources related to their power factor correction capacitors. ABB offers information on their power factor correction capacitors. Siemens provides details on their power factor correction capacitors. Schneider Electric offers information on their power factor correction capacitors. To understand power factor, it is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amperes. Real power is the power that performs actual work, while apparent power is the product of voltage and current. A power factor of 1 indicates that all of the apparent power is being used to perform work, while a power factor less than 1 indicates that some of the apparent power is not being used to perform work. This wasted power is called reactive power, and it circulates between the source and the load, increasing current flow in the system. Low power factor can cause several problems, including increased energy costs, reduced system capacity, voltage drops, and increased equipment heating. Power factor correction involves adding capacitors to the electrical system to supply reactive power. These capacitors act as a source of reactive power, reducing the amount of reactive power that must be supplied by the utility. By reducing the amount of reactive power flowing in the system, power factor correction can improve power factor, reduce energy costs, increase system capacity, improve voltage, and reduce equipment heating. Capacitors are rated in kilovolt amperes reactive. The size of the capacitor bank needed for power factor correction depends on the amount of reactive power that needs to be supplied. This, in turn, depends on the load's power factor and the desired power factor. Power factor correction capacitors are typically installed at the load, such as at motors or other inductive equipment. This minimizes the amount of reactive power that must flow through the electrical system. Power factor correction capacitors can be installed individually or in banks. Individual capacitors are typically used for small loads, while capacitor banks are used for larger loads. Capacitor banks may be fixed or switched. Fixed capacitor banks provide a constant amount of reactive power, while switched capacitor banks can be adjusted to provide the appropriate amount of reactive power based on the load. The selection of power factor correction capacitors depends on several factors, including the load's power factor, the desired power factor, the system voltage, and the harmonic content of the system. It's essential to select capacitors that are rated for the system voltage and can withstand the harmonic content of the system. Harmonics can cause capacitors to overheat and fail. Power factor correction capacitors must be installed and maintained properly to ensure safe and reliable operation. Capacitors should be installed by qualified personnel and inspected regularly. It's important to ensure that the capacitors are properly grounded and that the connections are tight. Capacitors should also be protected from overcurrent and overvoltage. The benefits of power factor correction include reduced energy costs because utilities often charge customers with low power factors a penalty. Improving power factor reduces the amount of reactive power that must be supplied by the utility, which can lower energy bills. Increased system capacity is another benefit because improving power factor reduces the amount of current flowing in the system, which frees up capacity on transformers, conductors, and other equipment. Improved voltage, which is another benefit because improving power factor reduces voltage drops in the system, which can improve the performance of voltage-sensitive equipment. Reduced equipment heating, which is another benefit. Improving power factor reduces the amount of current flowing in the system, which reduces equipment heating and extends equipment life. Several techniques can be used to improve power factor, including using synchronous motors because synchronous motors can be operated at leading power factor, which can help to offset the lagging power factor of other loads. Minimizing idling equipment because idling equipment consumes reactive power, which reduces power factor. Reducing voltage because reducing voltage reduces the amount of reactive power consumed by inductive loads. Installing harmonic filters because harmonic filters can reduce the harmonic content of the system, which can improve power factor. Power factor correction is an important aspect of electrical system design and operation. By improving power factor, it is possible to reduce energy costs, increase system capacity, improve voltage, and reduce equipment heating. The IEEE standard 519.2014 is a crucial reference for harmonic control, which directly impacts power factor. Harmonics are distortions in the voltage and current waveforms that can cause various problems in electrical systems, including reduced power factor. The standard provides recommendations and requirements for limiting harmonic levels in electrical power systems. Understanding and adhering to this standard is vital for maintaining good power factor and ensuring the reliable operation of electrical equipment. The IEEE Standard 18.2017 provides guidelines for the application, installation, and testing of shunt power capacitors. These guidelines are essential for ensuring that capacitors are properly selected and installed to provide effective power factor correction without causing any adverse effects on the electrical system. It covers various aspects, including capacitor sizing, location, protection, and maintenance. When selecting power factor correction capacitors, it is essential to consider the following factors. Firstly, the load characteristics. The type of load and its operating characteristics will determine the amount of reactive power that needs to be compensated. Secondly, the system voltage. The capacitors must be rated for the system voltage to ensure safe and reliable operation. Thirdly, the harmonic content, because the capacitors must be able to withstand the harmonic content of the system to prevent overheating and failure. Fourthly, the ambient temperature. The capacitors must be able to operate within the ambient temperature range to ensure proper performance. Fifthly, the altitude, because the altitude can affect the capacitor's performance. Sixthly, the installation location, because the installation location can affect the capacitor's temperature and exposure to environmental factors. When installing power factor correction capacitors, it is crucial to follow these guidelines. Firstly, ensure proper grounding to prevent electrical hazards. Secondly, use appropriately sized conductors to carry the capacitor current. Thirdly, provide overcurrent protection to protect the capacitors from faults. Fourthly, install disconnect switches to isolate the capacitors for maintenance. Fifthly, provide adequate ventilation to prevent overheating. Regular maintenance is essential for ensuring the continued performance of power factor correction capacitors. Maintenance activities should include firstly, visual inspections, checking for signs of damage or deterioration. Secondly, electrical testing, measuring the capacitor's capacitance and insulation resistance. Thirdly, cleaning, removing any dirt or debris that may accumulate on the capacitors. Fourthly, tightening connections, ensuring that all connections are tight and secure. Fifthly, replacing defective capacitors, replacing any capacitors that are found to be defective. It's important to remember that power factor correction is not a one-size-fits-all solution. The optimal approach will depend on the specific characteristics of the electrical system and the loads being served. Consulting with a qualified electrical engineer is recommended to determine the best power factor correction solution for a particular application. Furthermore, the cost of power factor correction should be considered in relation to the benefits. While power factor correction can reduce energy costs and improve system performance, the initial investment in capacitors and installation can be significant. A cost-benefit analysis should be performed to determine whether power factor correction is economically justified. Power factor is a crucial parameter in electrical power systems, affecting efficiency, capacity, and overall performance. Understanding power factor and implementing appropriate correction techniques is essential for minimizing energy waste, reducing costs, and ensuring the reliable operation of electrical equipment. The resources mentioned, including technical books, IEEE standards, technical papers, online resources, and manufacturer's documentation, provide valuable information and guidance for engineers and technicians involved in power factor correction. In addition to the resources already mentioned, it is also helpful to consult with experienced electrical engineers and technicians who have expertise in power factor correction. They can provide valuable insights and practical advice based on their real-world experience. Furthermore, attending industry conferences and workshops on power factor correction can provide opportunities to learn about the latest technologies and best practices. Networking with other professionals in the field can also be beneficial for sharing knowledge and experience. Power factor correction is an ongoing process that requires continuous monitoring and evaluation. The power factor of an electrical system can change over time due to changes in load characteristics or the addition of new equipment. It is important to regularly monitor the power factor and make adjustments as needed to maintain optimal performance. Power factor penalties can significantly impact electricity bills, especially for industrial and commercial consumers. Utilities often impose penalties for power factors below a certain threshold, typically 0.9 or 0.95. These penalties are designed to encourage consumers to improve their power factor and reduce the burden on the utility's transmission and distribution system. Power factor tariffs can be structured in various ways depending on the utility. Some utilities charge a flat fee for low power factor, while others use a sliding scale that increases the penalty as the power factor decreases. Some utilities also offer incentives for consumers who maintain a high power factor. The cost of power factor penalties can be substantial, especially for large industrial facilities with high electricity consumption. Therefore, it is essential for consumers to understand their utility's power factor tariff and take steps to avoid penalties. Power factor correction can not only reduce power factor penalties but also improve the overall efficiency of the electrical system. By reducing the amount of reactive power flowing in the system, power factor correction can lower transmission losses, reduce voltage drops, and free up capacity on transformers and conductors. These benefits can translate into significant cost savings over the long term. In addition to capacitors, other technologies can be used for power factor correction, such as active power factor correction devices. Active power factor correction devices use electronic components to actively shape the current waveform and improve power factor. These devices are typically more expensive than capacitors but can provide better performance in certain applications, such as those with highly nonlinear loads. Power factor correction is an important consideration for electrical safety. Poor power factor can lead to increased current flow, which can overload conductors and equipment, increasing the risk of overheating and fire. Proper power factor correction can reduce current flow and improve electrical safety. Power factor correction can also improve the stability of the electrical grid. By reducing the amount of reactive power flowing in the system, power factor correction can help to stabilize voltage and frequency, which is particularly important for systems with large amounts of renewable energy generation. Power factor correction is a key enabler for the integration of renewable energy sources into the electrical grid. Many renewable energy sources, such as wind turbines and solar panels, have variable power factors that can impact the stability of the grid. Power factor correction can help to mitigate these impacts and ensure the reliable operation of the grid. The design and implementation of power factor correction systems require careful consideration of various factors, including the load characteristics, system voltage, harmonic content, and cost. It is important to consult with qualified electrical engineers and technicians to ensure that the power factor correction system is properly designed and installed. Power factor correction is not a static process, but rather an ongoing process that requires continuous monitoring and adjustment. As load characteristics change over time, the power factor of the system may also change, requiring adjustments to the power factor correction system. Power factor correction is an essential aspect of modern electrical power systems. By improving power factor, it is possible to reduce energy costs, increase system capacity, improve voltage, reduce equipment heating, improve electrical safety, enhance grid stability, and enable the integration of renewable energy sources. The resources mentioned, including technical books, IEEE standards, technical papers, online resources, and manufacturers' documentation, provide valuable information and guidance for engineers and technicians involved in power factor correction. It's crucial to stay updated on the latest technologies and best practices in power factor correction to ensure optimal performance and reliability of electrical systems. Power factor correction is particularly crucial in industrial settings where large inductive loads such as motors, transformers, and lighting systems are prevalent. These inductive loads consume reactive power, leading to a lagging power factor. Implementing power factor correction in industrial facilities can significantly reduce energy costs and improve the overall efficiency of the electrical system. In addition to the benefits mentioned earlier, power factor correction can also improve the power quality in industrial facilities. Poor power quality can lead to equipment malfunctions, reduced productivity, and increased downtime. Power factor correction can help to mitigate these problems by reducing voltage sags, harmonic distortion, and other power quality disturbances. Power factor correction is not only beneficial for large industrial facilities but also for smaller commercial and residential buildings. Even in these settings, inductive loads such as air conditioners, refrigerators, and electronic devices can contribute to a low power factor. Implementing power factor correction in commercial and residential buildings can reduce energy costs and improve the overall efficiency of the electrical system. Power factor correction can be implemented using various methods, including capacitor banks, synchronous condensers, and static VAR compensators. Capacitor banks are the most common and cost-effective method for power factor correction. They consist of capacitors connected in parallel to the electrical system. Synchronous condensers are rotating machines that can generate or absorb reactive power. They are typically used in large industrial facilities where a high degree of power factor correction is required. Static VAR compensators are electronic devices that can provide dynamic power factor correction. They are typically used in applications where the load is highly variable or where there are significant harmonic distortions. The selection of the appropriate power factor correction method depends on various factors, including the load characteristics, system voltage, harmonic content, and cost. It is important to consult with qualified electrical engineers and technicians to determine the best power factor correction solution for a particular application. Power factor correction is a dynamic process that requires continuous monitoring and adjustment. As load characteristics change over time, the power factor of the system may also change, requiring adjustments to the power factor correction system. Modern power factor correction systems often incorporate sophisticated monitoring and control features that allow for real-time adjustment of the power factor. These systems can automatically adjust the amount of reactive power compensation to maintain a desired power factor, even as the load changes. Power factor correction is an important aspect of sustainable energy management. By improving power factor, it is possible to reduce energy consumption, lower greenhouse gas emissions, and conserve natural resources. Power factor correction is therefore an essential tool for promoting energy efficiency and environmental sustainability. In conclusion, power factor correction is a critical aspect of electrical power systems, offering numerous benefits including reduced energy costs, increased system capacity, improved voltage, reduced equipment heating, improved electrical safety, enhanced grid stability, and the integration of renewable energy sources. The resources and information provided offer a solid foundation for understanding and implementing effective power factor correction strategies.